Hello everyone, welcome to my channel. This is the first video of the series on gradients editing on the fly. Now, this is the part one of the video. This video focuses on the overall model training workflow. So first, a few words about gradient editing. We know that the gradient descent algorithm itself is widely used in training deep learning models, and it has been very widely used to train good deep learning models due to its generalization performance. And the reason seems to be specifically due to the algorithm itself, which is stochastic gradient descent. Now, this series of videos focuses on how to edit the gradient themselves. The most common place we see gradients being edited is the gradients is the clipping the value of the gradients, which is a built-in function in PyTorch and also in TensorFlow. However, we think that it is also possible to edit the gradients in other forms, like throwing in some noise, doing some addition or multiplication. And this is why we make this video. And as this is part one video, we focus on the fundamentals, which is the overall model training process. And later, we will focus on each specific components, namely the data, the model, the cost, and optimization, and then dive into more advanced editing of the gradients. So in this video, as you can see, this is a Google Colab Jupyter notebook, and you can refer to the link below to reference this notebook. For now, we just focus on the workflow itself. So as you can see, I have imported some libraries at the beginning. So this is usually what we do in terms of setting up the basics. And also I have here the setting of the seed to 8. So this is to ensure the results you see down below is fully replicated. And as we move down, as you can see that there's this graph, which I draw here. This is specifically illustrates the 4 components of a typical model training process. So first one is the data. Now, typically especially in a supervised learning setting, we have the data which consists of 2 parts, the input features and the target label. So the input features is usually the features that are contained by the data themselves, right? For example, if you're looking at a picture, then it usually consists of like, for example, 28 by 28, which is just a simple, for example, digits image from the MNIST data set itself, which we'll be using later. And each pixel in the image can be thought of as a feature that's embedded in the data itself. So features are themselves sort of the signals in the data, and these are something usually we can do something about that to augment the data itself, which also called feature engineering. For example, if the data has a shape of 10 and 20. So what this means is that we use 10 to represent the first dimension of the data, which is the size. Now it could be 10 images, right, or 10 data points. Now what 20 represents here is the number of features for each data point. For example, for each observation or each data point, we have 20 features, right? Each feature measures certain a dimension or certain perspective of the data. So sometimes we think that the 20 features themselves are not enough. So sometimes we may do some explicit feature engineering to make it, for example, to a size of 10 by 40, right? So with additional 20 features, which are manually sort of engineered, crafted, and then put in the data. So now the data size increases to another dimension. But this is not really, so this is also often done in practice, right? It lets the model learn more easily because we have extracted explicitly the features, the important signals that could be important for the model training purpose. So now, as we move to the right, now what's being used by the model in the first place is other features. And now as the features move into the model, right? So these are what's the sort of where the main magic happens, right? So the model is gonna turn the features themselves into a prediction. So think of the model is like a function that turns some features to some predictions. Now the predictions themselves are also point-wise for each data point. So meaning we will have 10 predictions, right? Because I have 10 data points and it's gonna have one column. So this is row level, this is column level. Why is it is one column? It's because the prediction itself, in this case, we're assuming is scalar value. So just one prediction, one single value for each data point. So if we zoom in on the model parts, we have the parameters and architecture. So the parameters are sort of the components of the model. It is what it consists of, right? So it could be 10 parameters, it could be 20 parameters, it could be even millions of parameters. So this is also usually a model with a bigger model would have more parameters, right? So this is also another sort of indicator of the complexity of the model. So these are the components. If I have more components by the model, then the model is going to be more flexible to learn potential patterns in the data, and then it's going to learn this data patterns more easily. But without maybe a risk of overfitting, right? You may be just memorizing the pattern of the data, the pattern in the features, and then not really generalizing to the feature data sets. So these are the parameters. We're going to use them to multiply with the features, and then in certain way. So the rule that governs how these features, these parameters, and these parameters interact with each other is through the architecture. So the architecture basically governs how the information interacts and then flow across the model, right? So it's sort of a governing system. We'll talk about more of this, how this look like in codes later. So now basically what the model does is to produce a prediction, right, point-wise, and then the label-wise, we also have 10 by 1, which means we have 10 labels, right? And then which each of them is a scalar value, so it's 10 by 1. So now what cost, if we move down, what cost here represents is it's gonna take the prediction and then take the true label, right, the true targets, and then produce a single cost, which is if I put it explicitly here, it's just 1 by 1, right? Just a single value could be 25, which is the cost. Cost could be root mean square error in regression, or coarse entropy in the classification case. But the explicit value depends on how we define the cost. Now, finally, after deriving the cost, we will go back through the application optimization procedure. So what optimization does in this case is to try to fine-tune our parameters, right, in a way such as the cost itself is minimized. So I want it to minimize to, for example, 0, right? So usually we define a cost to be a non-negative number, and of course the minimum value is 0. So I want to fine-tune parameters such as it produce another prediction, right, and then gets another cost which is lower than the current 25. So that's the overall objective of the training process. And what's following the notebook is that we're gonna code in practice what these 4 components represents: the data, the model, the cost, and also the optimization process, which is using the stochastic gradient descent. In this case, gradient descent because we're gonna, it's more sort of a general algorithm, and we're gonna provide example on how training one iteration works. So we're gonna not looking at, for example, in the beginning, we just diving components by components, and then look at one simple example. And then following, we're going to look at the different ways to create the gradients, for example, and then how to mask the gradients, how to do the gradient perturbation, which is to adding some noise, and also replace certain elements of the gradient themselves. And this could be an interesting exercise to do to see how we can potentially touch the gradients. Okay, so that's it for this video. Thanks for watching, and I'll see you in the next video.